Hello everyone, I am Deleep, a faculty member in the Department of Electrical Engineering, IIT Madras. Welcome to this talk titled From Electron to Electrical Engineering. Let me start with a disclaimer, as some of you may not know me personally or professionally. I am not a professional historian. I am only an amateur who is interested in the area of history of ideas and history of science and technology in particular. I have used mostly secondary and tertiary sources to prepare this talk. Let me clarify what that means. The book on the left is William Gilbert's De Magnete, which was published in the year 1600. It was written in Latin. We will see more about this book later. That is an example of a primary source. The second one from the left is considered as a classic reference book on electricity in the 17th and the 18th centuries by Professor Heilbronn. That's a secondary source. Books like this are mostly written by professional historians who refer to archives and have the ability to read original contribution written in multiple languages like Greek, Latin, French, German, etc. Third book shown here is written based on primary and secondary sources. I was also surprised to see a book on this topic to young children. I recommend this one to those electrical engineers who are looking for a book as a gift to young children. This talk is made mostly based on secondary and tertiary sources. I have given them as footnotes in respective slides. Let me show you a cartoon before showing you the outline of this talk. This cartoon was published by the UK-based Punch magazine in the year 1881. There are two giants, one white and another black. Both these giants, they look worried and asking what would this baby grow to. The white giant is steel and the black giant is coal. Both powered the first industrial revolution by providing a new source of energy and power. Please take a close look at the baby. He is electricity. It looks as if the baby is drinking from a feeding bottle. But on close observation, you will see that this wonder kid is blowing and filling a bottle of energy. This talk is about the genesis of this baby, and I will trace his history, and we will come back to this year of 1881 at the end of this talk. Now, let us look at the outline. First, I will discuss about electricity and magnetism before the era of William Gilbert, whose book we saw in the last slide. Next, we will see some of the early electrical machines. Next, I will discuss some of the early efforts on mathematization and quantification of electricity. The era of galvanism and electromagnetism will be discussed next. Then I will discuss the important era of cable telegraphy, which laid the foundation of electrical engineering as a profession, and some of the early efforts in creating the first electrical engineering standard. Finally, I will conclude by taking a look at when, where, and how academic programs in electrical engineering were started. Now, let us look at what literature is available on electricity and magnetism before the early modern era. We have studied in the school textbook that ancient Greeks knew about the Amber effect. As you can see in the lower right, here is a piece of amber. Amber is fossilized tree residue. You can see an insect which is trapped inside this piece of amber. The Greek word for amber is Elektron, which is used in the title of this talk. It seems Thales, an early Greek philosopher who lived in the 6th century before Common Era, knew that rubbed amber could attract light particles like feather. So here you can see a Greek postage stamp with Thales and a piece of amber and a feather. We know about Thales from the writings of later Greek philosophers like Aristotle. Coming to lodestone, lodestone is magnetized iron ore. Many of us might have heard about the legend of nails in the boot of a shepherd that flew towards a stone in Magnesia. The temptation to assign gods or spirits for any strange effect came effortlessly to the ancients. Since lodestone can move iron, people thought that it has got a soul. We can see some of the first non-theistic or rational explanations in the writings of Plutarch that attraction is due to the action of tiny particles which are emanating from lodestone or amber. These particles push air and that suction draws in iron or feather. Compared to lodestone, amber needs rubbing to release these small particles. Magnetism was considered as an occult property in a system of ancient medicine that is based on sympathies and antipathies. People thought that the magnetic property of attraction helps in seducing people. So, Romans used powdered lodestone in preparing love potions. Coming to Middle Ages, there is an account of Peter Peregrinus in 13th century Common Era who did experiments with lodestone. That era also saw the emerging use of lodestone in compass. But one can say that there was very little progress in the understanding of electricity for almost 2000 years. Now, let us take a look at the status of present-day Europe in early Middle Ages. For administrative reasons, Roman Empire was divided into a Greek-speaking eastern part and a Latin-speaking western part. After its fall, those areas under the western part were called as the Latin West. In the early ages, scholars of the Latin West knew very few of the works of Aristotle. However, Arab scholars who were closer to the Greek East have translated virtually the entire body of writings of Aristotle from Greek to Arabic. These works were translated from Arabic to Latin in the 11th and 12th century Common Era. This helped scholars like Albert the Great and his famous disciple Thomas Aquinas to create a synthesis of Aristotelianism and Catholic theology. The portions of Aristotelianism which led to contradictions with the main tenets of the Catholic theology were condemned by the Bishop of Paris in the year 1277 Common Era. This was a worldview of the Latin West for the next 300 plus years. The first Western universities were founded in the 12th century. Natural philosophy taught in those universities dealt with the causes and principles of normal course of nature. The main approach to create knowledge in those days was through deductive reasoning. In the hierarchy of knowledge, theology was considered as the queen, followed by philosophy, which was her handmaiden. Experimental methods and applied mathematics, they were given lower status or considered as unreliable. Experimental methods were used mostly by magicians, and mathematics was used by peoples like navigators, surveyors, mechanists, or merchants. For those people, a discipline like mathematical physics was a contradiction in terms. However, discoveries and observations in the 15th and 16th century showed the limitations of this worldview. Francis Bacon grew up in late 1500s in that world. He later became the Lord Chancellor of England. Although he is a very important person in the history of science, I am sure very few students of science and technology might have heard about it. That is because he has no discovery or invention to his credit. In spite of that, Thomas Jefferson the later President of United States, called Francis Bacon, Isaac Newton, and John Locke as the three most important persons lived in the 17th century. Let us see what was Bacon's claim to fame. Francis Bacon was the first major proponent of experimental philosophy. He exhorted natural philosophers to adapt methods from magicians and actively seek new knowledge. Bacon firmly believed that this new knowledge would lead to a better human life. He also proposed to create institutions of research. The irony was that perhaps the only experiment Bacon ever did led to his death. The title page of one of his books is shown here in the lower right. So here you can see two pillars. Those are the pillars of Hercules at the Strait of Gibraltar, which stood at the edge of the known world. The message of the picture is we have to sail beyond the existing world or the existing knowledge. We call the period 1572 to 1706 as the age of scientific revolution. 1572 was the year when people observed a new star in the sky. It was actually a supernova. Until then, as per Aristotelian physics, no change could happen in the celestial sphere where stars reside. There was no concept of birth or a death of a star. 1706 is the year when the first edition of the Newton's book Optics was released. During this time, people became bolder to actively question nature under a set of artificial conditions imposed by the experimentalist. Instruments like telescope, air pump, microscope, etc. were invented. People considered the possibility that the authority could be wrong than the individual. This period also saw the rise of research societies and academies like the Royal Society and the Paris Academy. Having said about Bacon, let us now meet William Gilbert, who was one of his contemporaries. Gilbert got his doctorate in medicine and later became the chief physician of Elizabeth I. He is now considered as a founding father of the experimental science. I would say he rebooted the experimental science. Others like Archimedes, Ibn al-Haytham, Peter Peregrinus also did experiments before Gilbert. But their enthusiasm and experimental culture was not sustained by others living in the society and their subsequent generations in those civilizations. Gilbert coined the name electrics for a wide range of materials which showed the amber effect. His main publication, as we saw earlier, was The Magnetic. Almost 93% of the contents of that book were on magnetism and the remaining on electricity. It was widely believed since the time of Pliny that magnetic properties of lodestone could be influenced by garlic and goat's blood. Ship captains refused to load garlic as it was believed that it might affect the functioning of the compass. Similarly, people thought that goat's blood, which is red in color, can increase the strength of lodestone, which is also slightly reddish in color. Gilbert experimentally showed these beliefs wrong in his book, The Magnet. Though Gilbert is remembered as a father of modern electrical sciences, in his book, he actually tried to show static electricity and magnetism as two completely different or unrelated mechanisms. He marshaled these observations to support his claim. For example, a rubbed amber could attract many light substances. On the other hand, lodestone is very selective and it attracts only iron. I'm not sure people in those era knew about nickel or cobalt. Lodestone and iron are like a monogamous pair. This effect of static electricity disappears after some time. On the other hand, the magnetic attraction is everlasting. A piece of amber or other dielectric needs to be rubbed to activate it. For a lodestone, it doesn't need any kind of rubbing. Static electricity is affected by heat or moisture of the medium. To the best knowledge of the people in the 16th century or the 17th century, the magnetism was not affected by heat or moisture. One of the main contributions of William Gilbert was to show that one could arrive at natural truths by doing experiments with man-made models. So, as we saw in the last slide, this was against the prevailing belief. The problem he took was the magnetic dip. It was believed that lodestone points to the north direction because of the presence of the North Star. People also thought that the lodestone derives its power through the from the North Star. Though the North Star is up in the sky, it is often seen that the tip of the compass shows a vertical dip and points inside the Earth. Now we know the reason, as the magnetic flux lines don't always run parallel to the Earth's surface. So Gilbert took a spherical lodestone and he did experiments with thin wires, and he could reproduce the magnetic dip behavior. Hence, he concluded that Earth was a giant lodestone. Copernicus lived a few decades before William Gilbert. Copernicus thought the heliocentric system was economical and harmonious. There were no new observations which showed his model was superior over Ptolemy's model. So finally, Copernicus wrote, almost after around 20 years, he wrote a book, and he asked a Lutheran minister, Andreas Osiander, to supervise the printing of the book. Osiander, on reading the book, found out that there are many claims which is objectionable to the Catholic Church. So he inserted an unsigned preface that all the claims in this book are just mathematical hypotheses and not true descriptions of any physical reality. Copernicus died without seeing a final printed copy of his book. But in his book, he never suggested a mechanism on how the Earth moved around the sun. There were other people who had suggested heliocentric model before Copernicus. For example, like Aristarchus in Greece, and some people believe Aryabhatta also proposed a heliocentric model. But none of them suggested a mechanism how the Earth moves around the sun. This is important because, as in Aristotelian physics, there are four elements: air, fire, water, and earth. Earth being the heaviest, its natural place is at the center of the world system, as we see from normal day-to-day experience that all objects fall to Earth. In Aristotelian system, the planets and the stars, they are not made of same matter as Earth. So in a heliocentric system, one has a difficult task to explain the cause of the Earth's motion around the sun. For Gilbert, who believed in the truth of Copernicus system, thought magnetism showed a way for the motion of Earth. So if all the other celestial objects are also magnetic in nature, the magnetic force, Gilbert thought it could explain the motion of the Earth around the sun. Kepler took this argument further to explain the elliptic nature of planetary orbits. Kepler considered sun as a special magnet. It's almost a magnetic monopole. With its surface as one polarity, for example, in this case it is North Pole, entire surface is a North Pole, and the center is a South Pole, center of the solar sphere. So if one takes the divergence of magnetic field around the Kepler's model of sun, it won't be zero, but a finite number. Similarly, the north-south axis alignment of the planets are always fixed. So if the planet tries to move around the sun, as you can see, in this side of the orbit, the south pole of the planet is seeing the closer to the north pole of the sun. So there is an attraction towards the sun. On this side of the orbit, the sun sees the north pole of the planet. Okay, so there is a repulsion. So what happens is that the one side of the orbit is attracted towards the sun, and the other side of the orbit feels a repulsion. So this makes the orbit an oval or elliptical in shape. However, Kepler could not prove this mathematically. Magnetic Copernicism, it existed for a few decades until the rise of mechanical philosophy. Finally, this puzzle, as you know, it was finally solved by Newton and Einstein. So we saw that one cannot just replace a geocentric model with a heliocentric model without giving proper explanation to a lot of intuitive phenomena. For example, like objects on the Earth's surface, they don't fly off when the Earth moves around the sun. Similarly, if one throws a ball up, it returns to the thrower, not behind or ahead of the thrower. And another crucial evidence was the absence of stellar parallax. So all these require a new alternative to Aristotelianism. So mechanical philosophy was one such alternative which claimed all qualities of bodies and natural phenomena using matter and their motion. Mechanical philosophy was actually a modification of Epicurean atomism. They made it finally they made it compatible with the tenets of the Christian theology. Two major proponents of mechanical philosophy were Pierre Gassendi and René Descartes. One of the central principles of mechanical philosophy was prohibition of action at a distance. So any particle in motion should be moved by something in its close proximity. For example, Descartes invoked the presence of vortices to explain the motion of planets around the sun. Similarly, they invoked microscopic particles or effluviae to explain magnetism and static electricity. So here you can see how Gassendi and Descartes explain static electricity and magnetism. So the Gassendi, here you can see the effluvia. He is comparing this effect to a chameleon. So just like the chameleon emits its tongue, okay, so the effluvia, they are emitted or emanated from the electric bodies. So they go, it attaches to the small pores in the light object, and it will bring them back. So that's how Gassendi tried to explain the static electricity. Similarly, Descartes, so he also invoked this effluvia, but in order to explain North Pole and the South Pole, he tried to invoke that these particles have different shape. So the Earth emits screw-shaped particles from each pole. So from one pole it's a right-handed screw, from other pole it's a left-handed screw. So if a piece of iron ore or magnetite, it lies buried under the earth, okay, so these particles, okay, it goes through this piece of iron, so over time it gets magnetized. That's how they used to explain static electricity and magnetism. So keep in mind, okay, all these explanations are qualitative in nature. Okay, there is no, so the mathematization and quantification, that comes much later. Let us now take a small detour to learn how ancients thought about vacuum. Aristotelians rejected the existence of vacuum in nature. In fact, Aristotle gave many proofs why vacuum could not exist in nature. But it was observed in Middle Ages that suction pumps and siphons could not lift water beyond 34 feet. Torricelli, who was actually a disciple of Galileo, he used a denser liquid mercury and showed this height could be reduced to 76 centimeters. This height reduction was very convenient as it made it portable for doing experiments and demonstrations. However, people were very curious on what determines the height of Mercury or the water column, and also is there anything in the space above it. Torricelli showed the height of the Mercury didn't depend upon the shape of the tube, and also it is independent of the amount of space above it. In one of the most famous experiments in the history of science, Blaise Pascal, asked his brother-in-law to measure the height of the Mercury column at the base and as well as the peak of a mountain. It showed a difference of around 84 millimeters. All these observations made them to conclude that we are living under an ocean of air and its weight is supporting the height of the Mercury or the water. You may be wondering what could be the connection between all of this and electricity. People observed that if you shake a mercury barometer in the dark, one could see sparks in the Torricellian vacuum. They called it mercurial phosphorus, as they wrongly thought it was related to the same phenomena of phosphorus which also glows in the dark. We will come to more of this in the next slide. One of the major inventions at that time was air pump, an apparatus to create the vacuum. Robert Boyle showed electrostatic attraction happens inside air pump. The credit for creating a proto-electric machine goes to Otto von Guericke. He was the mayor of the city of Magdeburg and more famous for his experiment on Magdeburg hemispheres, which shows the strength of atmospheric pressure. He took a spherical glass vessel, put sulfur and minerals in it, and he heated the vessel. Once the sulfur got melted and condensed, he broke the vessel and he took out the sulfur globe. So here you can see the sulfur globe. He kept the globe on a stand and he kept some bits of paper at the bottom. He found that on rubbing the globe, it made it attract the paper pieces. He also saw repulsion and glow, but he didn't pursue it further. We can consider the sulfur globe as a proto-electric machine. The credit to create the first generation electric machine, it actually goes to a person by the name Francis Hauksbee. Francis Hauksbee was the chief experimentalist of Royal Society, whose his job was to make weekly experimental demonstrations. Isaac Newton was the president of the Royal Society at that time. Hauksbee was actually trying to create the sparks which was seen in the Torricellian vacuum without a mercury barometer. So what he did is that, he took a spherical glass vessel. He attached the spherical glass vessel to a contraption like this one. So so you can turn this wheel. It will start spinning the glass vessel. Then he evacuated this glass vessel. Then while the glass vessel, when you start spinning, he tried to rub using his hand. He rubbed the surface of the glass vessel. So if he did this experiment in a dark room, then he could see a purple glow. On a different version of the experiment, he replaced the spherical glass vessel with a long glass tube. Again, he evacuated the glass tube, and this time he mounted a wooden hoop with hanging silk threads like this one. So once you start the spinning the glass tube, as if he tries to touch it with the hand, so he saw this glass tube is attracting all these silk threads in an axial pattern. The person who really took these dazzling effects to masses was Stephen Gray. He came up with this famous flying charity boy demonstration. This was a pure public demonstration. A boy is selected from the audience and hung through silk ropes. His leg is connected to a Hauksbee leg electrostatic generation. This boy could attract bits of paper or flip pages of a book with his hand. Several others like William Watson, Jean Nollet in Paris, they created adaptations of this demonstration. So here you can see a version made by William Watson. So here what happens is that electric virtue is transmitted, which they call virtue instead of charge or something. So the electric virtue is transmitted from the electrostatic generator through the boy to a girl. Okay, this girl is standing on an insulated platform. So this girl could attract, or even though she is far away from the electrostatic generator, now she could attract bits of paper with her hand. So this was maybe the first demonstration, okay, or a human demonstration of electric conduction. Another demonstration developed by Professor George Bose in Prussia is the electric kiss. So here you can see a lady. She is connected to this electrostatic generator. She stands on a insulating platform. So once you energize the electrostatic generator, once you start turning it, so if a person comes near and tries to kiss her, both would get a shock. So truly, the entertainment was the first major application of electricity. Please keep in mind that this was also an era when women were not allowed or encouraged to enroll in colleges in large numbers. So still you could see women operating these machines and attending these demonstrations. There was only a thin line which separates an electrician who is a public performer and a charlatan. Instrument makers used to make these machines like the electrostatic generator. So for professional electricians, as well as wealth. So similarly, wealthy people, okay, they used to buy these machines as an addition to their cabinet or collection of curiosities. This era saw the transformation of natural philosophy from an arcane interest into a public science. Now we are going to see a remarkable invention which actually created a crisis among electricians. This was invented twice at two different places almost within a year. First, it was accidentally invented by Ewald Kleist in the year 1745 in Kamen, then a part of Prussia, but now in Poland. He was using a setup similar to this one. So here you can see an electrostatic generator. It is connected using a chain to something known as a prime conductor. So using this prime conductor, Ewald, okay, he was trying to electrify water. So here you have a glass bottle, and this glass bottle, okay, there is a nail, okay, there is a cork, a nail goes through the cork and touches the water, and this nail is connected to the prime conductor. So he tries to see what happens. He was trying to electrify the water. He got a shock when he touched the top nail. So he reported this event to 5 other people. So despite many attempts, only one was able to get a similar shock. So the crucial element which Ewald failed to notice and to inform others was that he was standing on a ground and he was holding the bottle in his hand when he was trying to electrify the water, as well as he was trying to when he got the shock. Peter Muschenbroek, he was a professor at the University of Leiden in Holland. He was told by Professor Bose, whom we saw in the case of electric keys, who developed that Bose got a small shock when he had tried to electrify water. So Professor Muschenbroek, luck arrived in the form of a friend, a lawyer. So his friend got a heavy shock when he tried to touch the top of the bottle while standing on the ground. Professor Muschenbroek clearly identified the need for standing on the ground, and he clearly communicated this effect to others. So due to the clarity of his communication, others could also make Leiden judge and felt the shock. So for the first time in history, there was a portable device which could store electric charge. Later, the jar was modified to have and inner as well as an outer metallic coating. It led to more forms of entertainment, as shown in the lower right. Here you can see the women, they are asked to form a ring. The performer, he holds the hand of the first lady here, and on the other hand you can see a Leyden jar. Then he is touching the outer conductor of the Leyden jar. Then he asks this lady to touch the inner conductor, or which is there on the top metal rod. When she as soon as she touches, everyone gets a shock, and then they jump in unison. Jean Ole performed this kind of an experiment in the front of French royals with a chain of people almost a kilometer long. Some physicians also started to use Leyden jars to give electric shocks. You can see here, you can see an electrostatic generator, you can see a Leyden jar here. They started to use Leyden jars to give electric shocks to those people with paralyzed limbs or other illness which were considered due to the poor flow of body fluids. So they thought that these electric shocks would stimulate the flow of the body fluids. But this invention actually created a crisis for theoreticians. The accepted wisdom in those days, which we also see later, was called the Dufay's rule. That in order to electrify an object, one has to insulate it from moisture or ground. Now, but here you have the outer metal of the Leyden jar has to be grounded to charge it, or one has to stand on the ground to draw a shock using the other hand. William Watson was one of the first electricians who realized electricity can travel only through a completed circuit, and earth could be a part of the circuit. One may very well say that the charging of a Leyden jar could be the first human-made circuit. Now, let us see how electricians made sense of these various observations and the new electrical machines. So, inspired from hydrology, the standard model of science was to ascribe invisible fluids as mechanisms for various phenomena. So that is why there were humors to explain diseases in Greek, Indian, Chinese traditional medicine, caloric for heat, phlogiston for combustion. Similarly, electric and magnetic effects were also thought to be the effect of fluids or effluvia. Compared to astronomy and mechanics, which were mathematized in 17th century, electricity and magnetism was a tougher beast. We have seen one of the very first rules in electricity proposed by Charles Dufay. So that the body to be electrified has to be insulated. In early days, people observed only attraction. The amber effect, which was known to Greeks, was only about attraction. Later, they found out that when two bodies attract, they start to repel after touching each other. So they found it happens in a sequence. So they called it as ACR. So that is attraction followed by conduction, then repulsion. The trouble for the theoreticians was how to explain repulsion and electrical conduction using effluvia. So hence, Charles Dufay proposed the two fluid concept in electricity. One is a vitreous electricity, other is the resinous electricity. So he said similar type of electricity, okay, it repels and opposite type attracts. For example, if you take silk and rub it with glass, right, the glass gets positive charge and the silk gets negative charge. So, and similar, if you take another piece of silk and if you rub it with amber, right, so the amber gets negative charge, the silk gets positive charge. So whether one is so vitreous means it is closer to the glass, resinous means it is closer to the amber. So whether one gets vitreous electricity or resinous electricity depends upon the relative position of that material in the triboelectric series. So this was first proposed by Wilke. So to that state of understanding came the Leyden jar. So Leyden jar, we saw that it violated the rule of Dufay. That, and also because you need to ground the outer electrode of the Leyden jar to electrify it. And also it was found that the Leyden jar could be charged backwards. That is, one could connect the prime conductor of an electrostatic generator to the outer electrode of a Leyden jar, provided one touches or ground the inner electrode. So the people, the effluvists, they were at a loss to explain how the glass can prevent the flow of effluvia, and at the same time how it gets electrified. So here comes Benjamin Franklin. So Benjamin Franklin showed that the charge storage of the Leyden jar, it doesn't depend upon the shape of the bottle, but can be seen on glass plates sandwiched between lead plates. So it was called as Franklin squares. So they were the first parallel plate capacitor. Franklin also proposed a single fluid hypothesis. So there is only one type of electric fluid. The excess or the deficiency of that fluid creates the polarity, like whether it's a plus or the minus. But people used to think a lot and pondered a lot about why does a minus and a minus repel each other. Some, like William Watson, he tried to measure the speed of electricity using long conductors. They found it traveled almost instantaneously compared to the speed of sound. The dualist camp versus the Unitarians. Okay, the debate whether the electricity is a two fluid or single fluid, that debate never got settled in one party's favor. As we know that there are positive charges and negative charges. Though the current through metallic conductors is through the flow of negative charges. So far, we have seen two applications of electricity. The first one was entertainment. The second is electrical therapy. The third one which we are going to see is lightning rod. A god is associated with lightning in every mythology, like Zeus, Jupiter, Indra. So the lightning is usually associated as a sign of wrath of God. This actually created a problem for churches or cathedrals in Western Europe when they became some of the tallest structures in a locality. It also created a theological problem to explain why God chose to hit churches if he is angry, and not why doesn't the God stuck at the residence of infidels or brothels or drinking taverns. So those were considered as the dens of evil. Hence, okay, they suggested an alternate explanation that lightning is due to the action of evil spirits. So in order to scare off demons, bell ringers were sent to ring the bell at the time of lightning. So this, as you can imagine, this caused many deaths. People actually saw a resemblance in the sparks caused by the electrostatic generators or the Leyden jar and lightning. So, for example, they conducted autopsies, okay, on small birds which were killed by Leyden jar discharge. Okay, so the body, okay, the dead body, okay, it showed a similarity by death caused by the lightning. So, an experiment was conducted in the French village of Marly in the year 1752. That village is in the outskirts of Paris by Thomas Deleep. So what Deleep was, he was trying to test Benjamin Franklin's idea that an elevated grounded conductor could offer protection. So this experiment showed the lightning and electricity is related. So this experiment, this happened a few months before the Franklin's more famous kite experiment. Fortunately, nobody got killed in either of these experiments. So, but despite of this observation, some people actually they were reluctant to install a lightning rod, as they don't want any protection against something which is natural and an act of God, and which they thought as an act of God. So a terrible accident actually happened in the year 1767 when lightning struck at the church of San Nazaro. the church, okay, it had stored gunpowder in its walls. So when when the lightning struck, the gunpowder exploded, resulting in the death of almost like 3,000 people, and 1/5 of the town was destroyed in that explosion. So finally, all churches they adopted the lightning rods. Let us take a small detour and see what is going on. What was going on with magnetism? The main use of magnets centered around navigation and people trying to make better and better compasses. So Edmund Halley and Robert Hooke were two people who lived at the time of Isaac Newton, but all their achievements got eclipsed by the work of Isaac Newton. Halley is well known today for the comet which he didn't even discover. He is also well known for coaxing Newton to work on gravity and right principia. One of the major problems in navigation was to identify properly the local longitude. The latitude compared to longitude, latitude was much easier because one could infer that by looking at the elevation of the North Star in the northern hemisphere. But there was no such simple way to calculate longitude. Several people suggested that the problem of the longitude could be solved using something known as a magnetic variation. So variation is actually the angle between the geographic north and the compass needle. So Edmund Halley, he did extensive measurements and he mapped the magnetic variation. For example, here you can see the Halley's chart of magnetic variation, which was made in 1701. So in this figure, you can see he has plotted lines of constant magnetic variation. So Halley was the first one to use this type of lines, which we use these days to draw isotherms or equipotential lines. So if the magnetic variation changes consistently as we go from east to west, right, then by measuring the magnetic variation, one could infer the longitude. But here you can see that happens only in some regions like this one, like 40 degrees south, right? For example, for a busier route like an England to the colonial states in North America, okay, you can see this is a single constant magnetic variation line. So you will see the same amount of magnetic variation when you start from Britain to the North America. So Halley showed that the use of this magnetic variation is only limited and you cannot use somewhere in the North Atlantic. So this problem actually was finally solved by the construction of marine chronometer by John Harrison in the year 1761. So as in the case of electricity, magnetism was also used for therapy. In fact, magnetism was more popular than electricity as it was less invasive and no electric shocks were involved. So the basic idea was to, by controlling the flow of magnetic effluvia, one could possibly control the illness. So this concept is actually similar to what is there even now in traditional medicine, that one could cure illness by trying to correct the imbalances of the humors. So here is one depiction of a therapy room. So here you can see a large wooden platform. So magnetic materials are kept inside the wooden platform. So the patients come and sit on it for some time. They chat there. They were very happy after the session. They were very happy and they thought it is actually indeed working. So one famous therapist in Paris was Franz Mesmer, from where the word mesmerism was originated. Mesmer first started with using lodestones to control the flow of magnetic effluvia. But later he came to the belief that he could control the flow of effluvia using bare hands, as shown in this figure. So some physicians who wanted to replicate the success of Mesmer, and there are some other people who were not happy with this therapy, right? So they made a lot of objections. So, but actually people believed in this healing, and there were some strong claims of healing. So finally, a royal committee was appointed. Okay, it was headed by Benjamin Franklin to arrive at the truth of this matter. So they found out that the magnet has no curative properties. So more than this, actually, they finally banned Mesmer, but so more than this one, actually the decision to ban Mesmer was more political, as people were worried. They worried that about his power, Mesmer's power to control the mind of others. They were also suspicious that whether Mesmer was taking advantage of women patients. The attempts to describe electrical phenomena, okay, so far we have seen, okay, even from the days of Rene Descartes, okay, so they have been qualitative in nature. So the electricity actually resisted the attempt for quantification and mathematization, although this has been successful in other parts of physics like astronomy or mechanics. So if you would like to do quantification, okay, you cannot just go and measure something, right? So we need existence of proper concepts, appropriate concepts before asking how to measure something. Also, we should be able to express these concepts mathematically. Once that is available, then only we can go and test. Okay, and then we could also refine those concepts using measurement. For example, many people had conjectured the electrostatic force or between the electric fluids depends as a 1 over r square dependence. For example, Joseph Priestley he suggested that. So many people thought, okay, there could be a resemblance between electrostatic force and the gravitational force. Some of the early attempts of mathematization, it was done by Franz Mesmer and Henry Cavendish. But it was Charles Coulomb who came up with an elegant experiment to measure it. Coulomb, he was actually a French military engineer who had a lot of field experience in constructing forts and other civil engineering structures. He had worked on problems in applied mechanics like friction, beams, torsion, etc. So what Coulomb did is that he used his expertise on torsional balance, and he made an apparatus to measure the force between two charged particles. So this is Coulomb, and this is his torsional balance here. So what he did was that, okay, so there are two balls here. Okay, there's a balance here. There are two balls. Okay, initially these two balls are together. So if you try to charge it, okay, so both balls, okay, they get equal charges. They start repelling. They repel. So then, so the equilibrium a position is when the electrostatic repulsion between these balls is balanced by the restoring force of the string. So, however, this method cannot be used for opposite charges. That is because if you try to bring the balls closer, they jump and stick together. So, in the case of attractive electrostatic attraction, he used a pendulum-based approach. So that's how he first showed the 1 by r square dependence. Volta was another electrician who came up with with another expression like the Q is equal to CV. So Volta used, okay, he didn't use the terminology voltage. Okay, he used tension instead. So although, okay, this is a very well-known expression. Okay, I haven't seen this expression named as Volta's law in textbook. Okay, compared to Ohm's law or something like that. So this work of mathematization was later carried forward by the later French physicists like Biot, Ampere, and Poisson. The last decade of 18th century saw a bitter fight between two camps based on a very sensational observation. So Luigi Galvani, he was actually a professor of medicine at the University of Bologna. So he started a new research field on the effect of electricity on muscular motion. So we have seen earlier that electric therapists, right, they started applying the discharge of Leyden jar to patients. So one day in his lab, so he accidentally touched the nerve of a frog, okay, dead frog, using with a scalpel. So what happened was that, okay, so that the frog, it twitched. At the same time, okay, there was an electrostatic generator. Okay, it also fired, and there was a spark in the electrostatic generator. So both these events happened at the same time. So he thought that okay, there is some connection between these two. So he thought that he discovered a new form of animal electricity. Okay, so people were familiar with the fish, the torpedo or electric eel. So what he thought that okay, so the muscles, okay, the muscles are like miniature Leyden jars. Okay, the muscles store narrow electric fluid and which gets discharged through metal conductors. The crucial piece which Galvani overlooked was that the electric current or the shock is produced only when two different metals touch each other through a moist environment. Here, that's a frog's leg. So, for example, yeah. So here you can see the leg of a dead frog. So this this frog is hung through a brass hook. So if somebody takes another metallic conductor which is not a brass and touches the brass hook and the leg of the frog, okay, so the frog will expand. That okay, it's not a frog. Okay, so the legs will get expanded, something like this one. So Galvani thought all these results are a confirmation about the animal electricity. But another fellow Italian, Alessandro Volta, he didn't agree with this conclusion. So Volta insisted that the electricity, whatever the phenomena which is happening, okay, it originated in metal contacts. So in order to prove his point, he decided to recreate the effect without the aid of a frog. So what he did was that he kept zinc and silver pieces separated by a cardboard piece which is soaked in saline water. So he stacked. Okay, so he stacked a number of this. For example, this is zinc, silver, zinc, silver, zinc, silver. So he created a stack of this one. Okay, in the form of a pie. Then when he tried to touch the top electrode with the bottom electrode, he got a shock. So, but there were other phenomena which was happening. For example, he failed to observe electrolysis. Okay, it was happening in the pipe. So what Volta did was that he communicated this observation to his peers and later demonstrated this in front of others at Royal Society and even in front of Napoleon. So the electrostatic generator, Leyden jar, and voltaic coil. Okay, they were the three main electrical machines invented in 18th century. The electrostatic generator or Leyden jar, it produced small currents at very high voltages. However, voltaic coil, it produces relatively larger currents at small voltages. The main crucial difference for voltaic coil is that it produces a continuous flow of current compared to transient discharge of a Leyden jar. So this was a very simple device. Okay, people could reproduce it using coins, right? Whether you have a copper coin or a zinc coin, okay, you reproduce it very easily. And within almost like 20 years, okay, people confirmed these findings in the entire Europe. So Volta tried to suggest a mechanism on how the current is produced in the pipe, but only few people cared about. Volta came up with the different versions of mechanism. Okay, but only few people cared about the mechanism, because here you have a new device which produces a continuous flow of electricity. So Humphrey Davy, he used a large pile to isolate, for example, to isolate potassium, sodium, and chlorine. Okay, and launched a new field of electrometallurgy. So this was the almost like the fourth major application of electricity. So we saw earlier, like for the first industrial revolution, it was powered by coal and steam. So similar to coal and steam, now you have a new source of power. So this actually eventually resulted in the beginning of the second industrial revolution, that is actually based on electrical technology and chemistry. Volta didn't apply for any patent. So even though this was invented by Volta, so generation of electric current using this chemical action, okay, it was called as galvanism. So the galvanism was actually thought to be closer to chemistry, while the static electricity was thought to be closer to physics. So for almost like a 20-year period between 1800 to 1820, people thought that static electricity, galvanism, and magnetism, they were actually three different areas. So here, okay, I would like to show you a painting. Okay, this painting is done by an artist Niccolo Barabino. This is actually painted on a wall of a private residence in Genoa, Italy. This painting is to celebrate the invention of their national hero Volta. So here actually you can see Volta. This painting is titled Triumph of Science. So here you can see science. This science is portrayed as this lady, excuse me, and obscurantism is lying dead, defeated here. So here you can see Volta surrounded by a galaxy of other scientists. So this painting actually looks like Raphael's famous painting, The School of Athens, which shows there are a lot of philosophers in that painting. So if you examine closely, okay, around Volta, so this is Volta. Here you can see Samuel Morse. Here you can see Leibniz. Here you can see Descartes. Here you can see Franklin. And actually there are two Voltas. Okay, so here's Volta again. So so this is a voltaic pile. So I found this painting in Alessandro Volta's biography. So then I contacted Professor Giuliano Pancaldi, who wrote that book, to see whether he has got a digital copy of this painting. So when I contacted him, Italy was under a severe lockdown due to COVID-19. So, but he was very gracious to send me this painting. So I thank Professor Pancaldi for sending me this image. Let us see one major impact galvanism made on literature. One can confidently say that no work of literature has done more to shape the way humans imagine science or technology and its moral consequences than Frankenstein by Mary Shelley. The story, okay, if you have, I'm sure most of you have read the Frankenstein. Okay, if you don't know the story is about a scientist, Victor Frankenstein. Okay, the Frankenstein is not in the original story, it's not a monster. The name of the scientist is Victor Frankenstein, who collected dead bodies and he stitched together to create a creature. Then finally he gave him life, and the story continues with the later consequences of that action. This story was actually conceived in 1816 when Mary Shelley was only 18-year-old. So on that year, Mary Shelley accompanied her husband Percy Shelley to visit their friend Lord Byron in Geneva. One night, Byron proposed that each of them, okay, should write a ghost story after some discussion. So the next morning, Mary came up with a story which was published in 1818. So once it got published, okay, people were curious about how Victor gave life to the creature. But if you look at the novel, okay, so the novel is very vague on this part. Okay, so here I've listed short the content of the copper I saw for the novel. So it just mentions that the Victor, okay, this Victor. So Victor collected the instruments of life around, okay, that is around me, and so the Victor, it's said by Victor, and I might infuse a spark of being into the lifeless thing. Okay, so that means he has got some instrument of life, okay, which can infuse a spark. That's all. But later, in the year 1831, okay, Mary Shelley wrote in that edition, Mary Shelley wrote a new introduction. So in that introduction, actually, Mary recalled their visit to Lord Byron in the year 1816. She revealed that actually the idea came to her after listening to the conversations between Lord Byron and her husband Percy Shelley. So Lord Byron and Percy Shelley, okay, they were discussing about the possible, discovering the principle of life, and about the experiments of Erasmus Darwin. Okay, Erasmus Darwin was the grandfather of Charles Darwin, and about the possible reanimation of a corpse using galvanism. Right. So that's how she got the idea, which triggered her to write this famous work. All right. So as I said earlier, actually the static electricity, galvanism, and magnetism, right? They were thought to be three different areas, at least in the the first 2 decades of the 19th century. The static electricity was closer to physics, the galvanism closer to chemistry. So most of the initial applications of galvanism were in electrolysis and electroplating. So people suspected there is some connection. There could be some connection between electricity and magnetism, because now they know the lightning is related to electricity, and they have observed that during thunderstorm or something, okay, so it affects the mariner's compass. But still, okay, so the people thought that electricity and magnetism as two different fluids. In the year 1820, Oersted, okay, he made a discovery that a galvanic current through a wire, right, it could create a deflection in a nearby compass. But okay, Oersted was still influenced by mechanical philosophy, so Oersted suggested that the passage of current, okay, it creates a swirling vortex around the space surrounding the wire. Okay, so that vortex is actually deflecting the compass. And also, yeah, they try to just like electrostatic attraction repulsion. Okay, they try to look at the dependence of force on geometry. Okay, so the people found out that it's very complex compared to simple 1/r square dependence of gravitational force or electrostatic attraction. So the exact relationship, right, it was later worked out by Biot and Savard, which is now expressed using a vector product. So this deflection of this compass needle, okay, that technique was used by Johann Schweitzer to create a galvanometer. Okay, so here now you have an instrument, okay, which could detect a current through any coil. Later in the second in the 1820, okay, Ampere, he showed that a current carrying solenoid acts like a bar magnet, and you can have repulsion or attraction between current carrying wires. So he worked out the force relationship between the current carrying wires, and he started the field of electrodynamics. Okay, for his work, Maxwell called him as the Newton of electricity. Finally, Michael Faraday, in the 1830s, he showed that static electricity, voltaic electricity, and the newly discovered magnetically introduced, he discovered electromagnetic induction. So magnetically introduced electricity, actually they are all same, right? So all show galvanometer deflection, they show similar amount of heating, they trigger same kind of electrochemical reaction and similar sensations on the tongue. It may be it may be amusing to know that the concept of resistance, actually it came almost 80 years later to electrical science than the concept of capacitance. Okay, so we saw earlier Volta, right, about the Volta's law, Q is equal to CV, but the Ohm's law came almost 80 years later. So George Ohm, he obtained an empirical relationship. Okay, he was trying to study the flow of current through conductors of different length. Okay, so he was using a basic voltaic cell, but he, as you can see, he got some kind of a logarithmic relationship. The problem was that, okay, he was using a voltaic cell whose current actually reduces with time because of the effect of polarization buildup. Later, he tried to do with a thermoelectric cell, right? And he obtained a new relationship. Okay, capital X equal to a small a over b plus small x. So this is something similar to I is equal to v over r, something like that. So Ohm later followed with a theoretical paper in the year 1827. Okay, so that stated the magnitude of current in a galvanic circuit varies directly as a sum of all tensions. Okay, tension we saw its voltage, and inversely as the entire reduced length of the circuit. Okay, so the reduced length means actually resistance. So, but unfortunately, Ohm didn't get much attention, and he didn't get due recognition. Okay, one possible reason is that, okay, it could be the obscurity of definitions and concepts then in use. Okay, for us now, okay, the Ohm's law looks very simple, right? But it's actually a relationship between voltage or tension, which is actually a concept from electrostatics, and current, which is a concept from electrodynamics. So this is one of the reasons why the Volta's law, Q is equal to CA, predated the Ohm's law, that V is equal to IR. So the Ohm's law was finally confirmed in experimentally confirmed in the year 1831 by Gustav Fechner. Later, Gustav Kirchhoff, he published the Kirchhoff's current law and Kirchhoff's voltage law in resistive networks in the year 1845. In the same decade, James Joule and William Thomson, they connected heat, energy, and work with the electrical concepts. So you may think like the relationship, the power, I square R and VI, they are, it's just a matter of, they are the same, but you have to keep in mind, it could be trivial, but to those people who are living in the middle of 19th century, that was a time when actually the concept of energy was being developed along with the first law of thermodynamics. So we saw one of the first major use of galvanic electricity was in electrometallurgy and electroplating. So I know the next application was actually there was a big demand for electric telegraphy. Now let us see how telecommunication was done before electric telegraphy. Right. So there are many ways by using pigeons or sending couriers on horses, but there were hardly any methods to convey messages faster than a messenger could carry them. Right. So in the late 18th century, a new system of optical telegraphy was developed by Chappé brothers in France to solve this problem. So here you can see it consists of 3 bars. One here, and here. So the orientation of these bars, the orientation of these bars could be adjusted by a system of pulley and levers. So this had actually 98 different positions. So one could adjust into 98 different positions, and 6 of those positions were actually reserved for service messages. So different alphanumeric symbols, you can see some of the alphanumeric alphabets and the numerals. So how it was, so these were encoded into the position of the bars. They also need to use encryption because anybody could see the position of the bars, right? And so the first line was set up in France between Lille and Paris. So this was almost like a 200-kilometer line. So between for the 200-kilometer line, you had around 15 stations. So once the position is set up, once the configuration is set up, so it is visible to the next station. They could see through a telescope or something. They put it down, then they made the same configuration. That's how the message is transmitted. So in the early days, it took almost like one hour to send a message across 200 kilometers. Not bad. So later, this network was expanded to cover the entire France. So this system worked well, unless there is unless there was a poor visibility condition like night, snow, fog, and rain. In fact, they were very happy with the system. Actually, this actually delayed the implementation of electric telegraphy in France until around mid 1850s. So also some of the first network problems actually were originated and they tried to solve in the system of optical telegraphy. Now let us see how people imagined about communicating using electricity. Please keep in mind this that is before nobody has developed any electric or electronic detector. So Ronald Francis, in the second decade of 19th century, he found out that you can do electric signaling, over long distance, like almost like hundreds of kilometers. So he set up a system at his home using 2 synchronous clocks. So there is one clock at the transmitter side, other clock at the receiver side. The second hand of the clock was modified. It moves over a system of a set of symbols. So if you want to transmit a letter A, so you send an electric signal when the second hand is over A. So as the clocks are synchronized, the receiver can read out the symbol on sensing the electric signal. So that is one way. Next one was using it's actually an electrochemical telegraph by Samuel Thomas. So the receiver is actually a collection of electrolytic cells, which is powered by a voltaic pipe. So a wire connects between the symbol key, for example, the symbol key here, from here to its corresponding electrolytic cell in the receiver side. So if you want to send any symbol, okay, you you choose appropriate symbol. A wire, a current is sent through the line of bubbles in that particular electrolytic cell. So that's how you can decode the message. So as you can see, only electro prototypes or few systems were developed. None of these methods were deployed for a mass use. Now let us see the early days of electric telegraphy. So the William Cook, okay, actually he was a person, okay, he was returning from British India. So on his way back, he attended a lecture on electricity at University of Heidelberg. So then he got this idea of sending messages using electricity. So on reaching Britain, he visited Professor Charles Wheatstone. So after many discussions, they came up with this idea of a 5-needle telegraph. So here you can see there is a needle here. Okay, this is similar to a needle in the galvanometer. So this needle could be deflected left or right depending upon the current. And the orientation of two needles, okay, it will decide the symbol. For example, you look at this needle, okay, so you follow the orientation of this needle, and the next deflected needle is this one, okay, so you follow this one, okay, so this configuration means, okay, so the transmitted symbol is V, letter V. So so finally they had to omit 5. It's a 5-needle telegraph, okay, so 5 alphabets were omitted. So they installed a 13-mile commercial, okay, 13-mile system. It was the world's first commercial system along the side of a railroad. Okay, so the development of the railroads actually helped the initial deployment of or acceptance of electric telegraphy. So, but as any technology, okay, there were a lot of skeptics. Okay, so what's a use? Okay, what good it can do? So interestingly, okay, so the application which caught the attention of skeptics was catching fugitives. So in those days, okay, it was a practice of pickpockets to escape in trains. But so once they got into a train, there was no way to outrun a train and reach the next station in time to catch them. So actually, telegraph helped here. So there was a similar case when a telegraph was also used to capture one who murdered his mistress and escaped in a train. So they caught him after receiving his description through telegraph. So these events, right, actually they caught the imagination of the public. So while developing the telegraph, actually the Wheatstone, he recognized the importance of Ohm's law. So the original work was published in German, and Wheatstone got it translated to English in the year 1841. So meanwhile, across the Atlantic, Samuel Morse also had this idea of electric telegraph, and he, in collaboration with Alfred Vail, he developed the Morse code. So you don't require a 5-needle telegraph. You have a Morse code system, and they also developed this single finger key system. They approached the US Congress for funding, and in a very close vote, actually, the US Congress approved the Washington-Baltimore line. So this was finally completed, okay, I think in 1844. So this line actually got public attention, okay, just like in Britain, okay, there were a lot of skeptics. So this line, the Washington-Baltimore line, got public attention when it could announce the name of Whig convention nominees by almost 1 hour. Okay, so there are two methods. Okay, so one they send it through the telegraph, other they send it through the usual means. So the message which was sent through the telegraph, it arrived almost 1 hour earlier than by any other means. The land telegraphy arrived in India in the year 1854. Sorry. So actually, telegraph, actually, it was a revolutionary invention, although we don't use it anymore. It truly annihilated time and space. Okay, so there was a big demand for news. It completely changed the way people people consume news, and similarly the business news. For example, here you can see this is a stock ticker. Okay, it was actually first invented by Edison. He made a lot of money from this invention. Finally, telegraph actually also helped Britain and France to make almost real-time strategic decisions in Crimean War. Okay, so Crimean War was the first one where telegraph was employed. So once the overland telegraphy it became very success, there was a growing need for the telegraph lines to cross the sea. So on overland, okay, so you could use tarred cotton to insulate the land lines, and only one needs to worry about the insulation at the telegraph poles. However, the cables, or it require a better insulating material for underground or underwater, because just outside the insulation you have the earth. So it was found that gutta percha was a good insulator. It's actually a tree product, which is it's like a natural plastic. It becomes soft on heating and it becomes hard on cooling. They found it abundant in Malay Peninsula, which was actually under British dominion. So in 1851, a cable was laid under English Channel. So similarly across Mediterranean, across the Baltic, and so there were, because those were all short distances. Okay, so people could lay telegraph cables or submarine cables in those. So there was actually a demand for people, so that okay, why can't we connect UK and the United States? So the Cyrus Field, actually he was a self-made man from New England who made a fortune in the paper trade. So he became a champion for the transatlantic cable. In the meantime, U.S. Navy found out that the route between so then the question is, where do you lay the cable? Okay, they found out the route between the Newfoundland and Ireland. It has a good flat seabed, but it was found that the submarine cables, okay, they suffer from the problem of retardation. Actually, this is the delay in RC circuits, which is now familiar to any 12th grade student learning physics. So here you can see two telegraph signals. Okay, one is a string of alphabets. Okay, the second one is dots and dashes in quick succession. So if you send this signal, okay, through different telegraph cables with a different RC time constant, you can see how the signal propagates. So this effect was first actually observed by Michael Faraday in 1830s. Later, William Thomson, he derived an expression and showed that this retardation phenomena, it actually depends upon the square of the length of the cable. So this was important for transatlantic cable, because that length of the cable is almost like 100 times longer than the English Channel cable. So the Wildman Whitehouse, okay, he was the chief electrician for the transatlantic project. Right? He was so he called the retardation problem and the law of squares by the William Thomson. Okay, he called it as a fiction made by the academicians in schools. Okay, so who are far from, okay, these academicians or people in university, they are very far. They're far from real engineering problems. Okay, he predicted that you won't see in their real life. So the work has started for the transatlantic cable. So in order to meet the deadline, what Cyrus Field, he ordered 2,000 miles of relatively thin cable. Okay, they were worried about the weight of the cable, so they used a very thin core, right? So Whitehouse, okay, the chief electrician, he did some tests and he declared the cable fit for service. So the cable laying, it started, and during its first attempt, what has happened? Okay, this they started in August 1857. The cable snapped. Okay, so they used two different ships. Okay, because the entire one ship was not enough to accommodate the entire length of the cable. So the ships returned, and the cable was left in the open at the docks for many months. Okay, so actually this resulted in the degradation of insulation. So finally, after the winter, okay, the ships returned next year with a better laying equipment, and in August 18, exactly after 1 year, okay, they completed the cable and connected between Ireland, the west coast of the Ireland, and east coast of the Newfoundland. So there was a big celebration, but they found out that the signals coming out were very garbled and very weak. So William Thomson, he designed a very sensitive instrument known as a mirror galvanometer to detect these kind of weak signals. So through this cable, actually the US President and Queen Victoria, they sent congratulatory messages for the successful completion of cable. But it took almost like 1 hour to send and detect 15 words using mirror galvanometer. So Wildman Whitehouse, he was impatient with all these things. So he said that I could overcome the retardation problem by increasing the voltage levels. So he sent signals with at higher and higher voltages. So, but finally, what has happened is that the higher voltages destroyed the insulation, and after the cable was declared dead after 1 week. A similar fate actually happened for another high-profile cable. Okay, so that was the plan to connect London to India. Okay, so this part of the cable was between the Suez Canal to Karachi. So now you have the failure of two high-profile cables. Okay, so a committee was set up to inquire about the failure of the cable. So in 1861, the Galton Committee, okay, it submitted the report. Okay, so it identified serious mistakes in design, manufacture, and handling of cables. It also stressed the importance of making accurate electrical measurements and quality control during manufacture and laying. It also suggested the committee, okay, it's the formation of the British Association Committee of Electrical Standards. Okay, let us take a small detour on measurements. In early day, physics was quite simple with only mechanics and astronomy. Then it got, as we saw it got complicated with the arrival of electricity and magnetism. Okay, so now you have, with the arrival of electricity and magnetism, you have new electrical and mechanical concepts. For example, we saw, right, we could measure the force, right? There's a symbol, the expression of force between between two charges in the electrostatic system. So one could define force, one unit of force, as one between two electrostatic unit of charges, or two current carrying conductors, or two magnetic poles. So depending upon whether you start with charge or whether you start with poles, magnetic poles, or whether you start with the electric current, you get different system of units. For example, you have electrostatic unit, electromagnetic unit, electrodynamic units. So physicists and electricians, actually they used different units. Each country had its own standard based on different materials, and there was no way to measure absolute resistance. But one can only compare using a Wheatstone bridge. In meantime, Wilhelm Weber and Gauss, okay, they did measurement of Earth's geomagnetism. So based on the experience gained from that work, okay, Weber actually proposed the concept idea of absolute units. That is, he wanted to reduce all measurements and express them in units of mass, length, and time. The idea is to relate electrical and magnetic concepts to force and energy in mechanics. But the people who are in the field, for example, like Wheatstone, okay, Wheatstone introduced a copper-based standard for resistance. For example, okay, you define the resistance as, okay, the resistance of a copper wire which is 1 foot long. Similarly, Werner Siemens, he suggested you take a glass tube of 1 millimeter in cross section, fill it with mercury. Okay, so that tube, the length of the tube is 1 meter. Okay, so that is 1 ohm. So these are all very arbitrary definitions. Okay, so that's the beauty of absolute units. And also, before 1857, all the cable contracts, they had specified only the weight or the gauge of the wire. There was nothing on the chemical purity of the material or the electrical characteristics. So William Thomson, actually, he was a professor at the University of Glasgow. So his research students and the cable engineers, okay, so they worked at his lab. Okay, so they realized the need for a highly pure copper core, right? And also they were worried about variation, okay, well, along the length of the cable as well as cable to cable variation. So during the Galton Committee hearings, okay, William Thomson suggested the adoption of absolute units. Similarly, Fleming Jenkins, okay, he was a cable engineer who later became the first chair of engineering at the University of Edinburgh. He also told the Galton Committee the need for is the standard resistance coil, right, with an official status and authority. That is because they need exact resistance standard to locate fault in the cable. So hence the British Association of the Advancement of Science, it appointed a committee for electrical standards. Okay, this committee included physicists, chemists, and cable engineers. So it started with 7 members in 1861, and 6 were added in 1862. So William Thomson, James Clerk Maxwell, they were some of the physicists. Okay, Maxwell joined in 1862, and Latimer Clark, Fleming Jenkins, they were the cable engineers. So the initial plan of the committee, or the mandate of the committee, was to come up with a standard for resistance. But later, after it was broadened to come up with the standard for other electrical concepts also. So Maxwell, Jenkins, Stewart, and Hawking, okay, they did careful measurements and came up with the Ohm standard in 1863. So in the meantime, actually Maxwell, before coming into this submarine cable work, actually Maxwell was working on electromagnetism before pulled into this cable work. So Maxwell had proposed a mechanical theory of light as waves in just like mechanical waves in elastic solid. He also had a mechanical theory of electric and magnetic forces. Okay, for example, in his mechanical model, okay, this is the wheel vortex, this is a vortex, and this is wheels. So in this model, okay, you can see this is a circulation. Okay, so this circulation is the magnetic field, and if there is any expansion or contraction in this direction, okay, that is due to electric field. Okay, because of this circulation, and so these wheels, okay, this will move through this gap. Okay, that's how the energy is propagated. So he had a completely mechanical model of either before coming into the working on the submarine cable. So Maxwell's work on this committee, British Association committee, led him to think more like an engineer. So he put aside this speculation about these vortexes. Those are unseen. Okay, one cannot observe these vortexes. So he decided to focus, just like an engineer, to focus on parameters which he could measure and control. So he dropped the vortex model of either in 1864, and he published a new paper that's titled A Dynamical Theory of Electromagnetic Field, okay, which is considered as the greatest scientific paper by Clerk Maxwell. So now in that paper he expressed his theory in pure electromagnetic form. So he completely avoided the mechanical things, the mechanical concepts. So finally, the British, okay, the new standard, the British Association Ohm, it was adopted by the big British companies, cable companies. Okay, they were the ones which were in the business, and they also made. Okay, the committee also suggested, and they made. Okay, they made the standard British Ohm here. Okay, so for customers, okay, they could buy the standard Ohm. So finally, a new cable, right? With all this understanding, okay, so they decided to make a new cable with improved conductivity, okay, so and insulation and strength, okay, and also with careful manufacturing and also the quality control in testing. So the cable laying again started in July 1865, almost 10 years after the first work. So in the previous attempt, okay, 10 years back, okay, as I said earlier, okay, the 2 ships were required to load the thinner cable. Actually, after 10 years now, actually they were lucky to have a big ship, okay, which could load the entire cable, the thicker and the heavier cable. This ship actually was the Great Eastern, designed by the legendary engineer Isambard Brunner. This ship actually was 5 times bigger than the next one in size. So they started laying from the Irish coast. However, actually the cable snapped after laying for 1200 miles. So they marked the location. They went back to the Irish coast, and then they started again from Ireland in 1866. Finally, they could finish their work in just in 15 days. So meanwhile, the snapped cable, okay, which went to the bottom of the ocean in the previous year, okay, so there it was lifted, it was spliced and connected. Okay, so then in 1866, actually there were two cables between Europe and USA. So when they tested it, they found it very good. Okay, so they could send 8 words per minute. Okay, with no repeaters. Okay, so ships in those days used to take almost like 2 to 3 weeks to take a mail from UK to USA. So similar, a London to India cable, okay, through the Red Sea was also completed in 1870. Okay, in those days, if you want to send a mail from London to Calcutta, it used to take almost more than 40 days. So for his services, William Thomson was actually he was knighted in 1867, and later he became the first scientist elected to the House of Lords. So today he is well known as Lord Kelvin. Here is again another cartoon which came in Punch magazine after the successful completion of Transatlantic Cable. Here you can see Neptune, the Lord of the Seas, blessing Uncle Sam and Britannia. So we saw the idea of cable, actually the transatlantic cable. It started in USA. The Cyrus Field was the champion for almost 15 years. Nevertheless, okay, it was actually Britain who supplied the science, technology, and the finance for transatlantic cable. Britain dominated cable telegraphy. Okay, it was considered as the most advanced high-tech industry of the day. So here you can see a picture of the cables owned by the Eastern Telegraph Associated Telegraph Companies. So here you can see all these wire, these connections. Okay, those are the submarine cables, and the red regions in this map. Okay, those are British colonies. So British colonies at different parts of the world. So that is why Britain had a lot of interest in laying it was in laying the telegraph submarine cables around the globe. All right. So in the early modern era, engineers or artisans, right, they used to learn the profession through an apprenticeship model. Okay, so if you want to become master in some area, so he typically okay, they used to work around 7 years as an apprentice before they can start a shop on their own. So it was actually France who first set up technical institutes, right, to create military engineers, like we saw in the case of Coulomb. So any non-military engineering work, okay, it was considered as civilian. Okay, that's the origin of civil engineering. So this model actually worked well for civil and mechanical engineering, which had also a relatively long history. But however, the science and the maths involved in the electrical engineering, okay, it was not something one could learn by observation or by hanging out on a shop floor. So as we saw, the electrical engineering, it evolved along with the rise of cable telegraphy. But later, more demand actually came from power and light industry, especially in Germany and US. So this transition, okay, you can see this change is reflected in the name of electrical engineering professional societies. The first electrical engineering society was Society of Telegraph Engineers, which was created in 1871. But however, it changed its name to Society of Telegraph Engineers and Electricians in the year 1880, and finally to Institution of Electrical Engineers in 1890. So to accommodate like the diversity now coming up in the electrical engineering profession. So similarly, the task of teaching electrical engineering courses, okay, there were no electrical engineering department. So the initial task of teaching electrical engineering courses, it fell on physics professors. So Technical University Darmstadt in Germany, it set up the world's first full department of electrical engineering in 1882. Similarly, Cornell and MIT set up their first full electrical engineering departments in the year 1888 and 1902, respectively. So, but later, if you look at now, in most places, now the electrical engineering department is bigger than the mother physics department. In India, the electrical engineering undergraduate program was first also started in an institute which later became the Jadavpur University in the year 1907. And actually, I found this information about. I looked a lot. I found finally I could get this information in this paper by Professor Vijay Murthy, which was published almost like 50 years ago on the status of electrical engineering education in India. Similarly, the Department of Electrotechnics in IISc, it started the PG program on electrical engineering in the year 1911. All right, before concluding, okay, let me show, as I said earlier, let me show another punch cartoon, okay, which was also published in the year 1881. So this cartoon was published around 6 months after the cartoon we saw on the second slide. But here it is different. Is that here is an artist who is who imagine a world run by electricity. So here you can see the same baby, right? So now you have the electric bulb here, and you can see the people who are working in the coal industry, okay, and the Victorian factories, okay, they're running away. So you can see a prediction of an air transport powered by electricity, London to Paris in 2 hours. And here you can see frozen beef from Australia transported to Britain and revived on its arrival in Britain using electricity. So similarly, some fruits and vegetables grown with the help of electricity. So you can check how many of these predictions were turned out to be true. So if you ask someone to define technology, right, it's very likely that they would say it is applied science. However, as we saw, if you look at electrical engineering, the links between electrical science and technology, it ran both ways in the 19th century. Each feeding of it. So, for example, like inventions like Leyden jar and submarine cable, right? Again, it improved the understanding of electrical theory. And similarly, scientists like Lord Kelvin, okay, they improved technology. So this is slightly different from what had happened for mechanical engineering. For example, in mechanical engineering, okay, so the new Coleman engines and the later Watt-Boulton engines, steam engines, okay, they were running for almost like 100 years, and people were even traveling in trains before the laws of thermodynamics were formulated. However, if you look at solid-state electronics, okay, it's a different picture, right? It is more in lines of technology as applied science. So the quantum mechanics was developed and was needed to develop solid-state devices. So if I try to recapitulate, okay, the first 5 applications of electricity were actually entertainment, electrical therapy, lightning conductor, electrometallurgy, and telegraphy in that order. Okay, here is a small take-home assignment. If you want to explore this field, further explore this field, so you don't need to submit these answers to me. Okay, so in this talk, okay, one may accuse me that my talk was Eurocentric. Okay, as the most of the people you have seen, maybe except from Benjamin Franklin, okay, they were from Europe. I am yet to see any descriptions or a non-theistic explanation of Amber effect or lodestone from early Indian literature. So Toby Huff, actually, in this book here, he had written about the reception of telescope in other cultures. So I am also curious to know whether curious or wealthy people in India living in 18th century, 18th or 19th century, they try to collect or make electrical machines. So I don't know whether there is any such evidence on the use of electrostatic generators, a Leyden jar, or a voltaic pile, which can be seen in Indian Science Museum. I have read about a person. Okay, his name is James Dinwiddie. He was a Scottish performer. He came to Calcutta. He gave lectures and a demonstration. He gave lectures on electricity. He gave demonstration on some early electrical machines like electrostatic generator and voltaic pile around 1800. Okay, so it was not it was soon, a few years later, after the invention of the voltaic coil. This talk was actually originally planned as from electron to electron. I thought maybe the two homophones, electron and electron, in the title may sound good, but actually the plan was to continue after the invention of voltaic coil and electromagnetism through the works of Faraday, Maxwell's cathode rays, and concluding at the discovery of electron by J.J. Thomson. But on a second thought, I thought maybe I made a course correction. So I thought maybe the path may be less appealing to electrical engineering students. So that is why I took a path through the electric telegraphy, the submarine cables, the development of electrical engineering as a discipline through the electrical engineering standards. So here is something you can do. Okay, before voltaic coil, actually Volta invented electrophorus, which was found to be a perpetual storage or source of charge. So the task for you is to find out how an electrophorus works. All right, so let me leave you with a quote by Benjamin Franklin. So this was from a letter which was sent by Benjamin Franklin to Joseph Priestley in the year 1780. It was 10 years before Franklin died. So in his letter, Franklin, you can see Franklin lamenting about he was born and lived too soon, right? I think he was expecting many interesting things to happen in electrical sciences and science in general, science and technology in general. So having learned about the history of electricity and maybe on further reading about the developments in the 20th century, you can also wonder and whether you were born too late or too soon or at the right time. Thank you for watching. I would be glad to receive your feedback.